Hello subscribers and my dear students, welcome to Learning Chemistry is Fun. Ready with another set of videos. Sorry for the long break. Entropy changes in the third law of thermodynamics is our topic for today. This we are continuing from part 14 of the heading or the series of videos on thermodynamics. If you do not have clarity on entropy changes, I would request you to go through the videos which have been previously posted on the same channel. Today we are talking about the phase changes, entropy changes which happen during the change of phase. Now change of phase you have been studying since your class 6, where you talked about melting or fusion, freezing, vaporization, condensation, sublimation. Now, entropy does change when one phase changes to another. In the case of solids, the particles are held together closely in a compact form. They are undergoing only vibrational motion. Liquid phase, when you heat it, the particles, they start moving away from each other. The randomness, the disorderliness of the particles increases. In the case of a gas, the randomness increases even further. So that means there are entropy changes taking place during change of phase. Now in order to define the various entropy changes, we just have to remember our delta S is Q reversible divided by the temperature at which the change is taking place. Now here the Q reversible will correspond to the enthalpy change taking place in each of the phase change. So when I'm talking about melting or fusion, the enthalpy of fusion will be involved. And here there is an increase in entropy. What about when I'm talking about the reverse process, liquid to solid? Does the randomness increase or decrease? Yes, it decreases. So what will happen is there will be a decrease in entropy. Same way, liquid to gas. It is called vaporization. So the enthalpy, the Q reversible will be equal to the enthalpy of vaporization, while the reverse process would be a negative value. Sublimation also takes place at a fixed temperature, at a particular temperature. So simply put, we can define the entropy of the transition. Transition means from one phase change to another, as simply the change in entropy for a particular process at a fixed temperature. So supposing you have to define entropy of fusion. Entropy change when 1 mole of, yes, fill in the blank, solid changes to liquid at what temperature does the change take place? Yes, at the melting point. So you can fill in the blank according to the transition you are talking about. Entropy change when 1 mole of liquid changes to gas at the, yes, boiling point is called the entropy of vaporization. Accordingly, you can put the subscript. So entropy of fusion, entropy of vaporization, entropy of sublimation. So the defining part of it becomes very easy. Same way for sublimation, the entropy change when 1 mole of the solid changes to gas or vice versa at a particular temperature. Coming to entropy change when there is a chemical process taking place. Now when it is a chemical process taking place, so we have reactants changing to products. So just like we did with enthalpy, if you remember, we did simply the enthalpy of the products minus the enthalpy of the reactants. The same principle applies over here. Enthalpy change for a reaction is the summation of the, not the enthalpy change, the entropy change. Apologies. Entropy change for a reaction is the sum of the entropy of the products minus the sum of the entropy of the reactants. Now please remember, because entropy is an extensive property. Extensive. Can you recall what we mean by extensive property? Give it a guess. Yes, something which depends upon the mass of the substance taken. That is why when we do the entropy over here, when we take the entropy of the products and the entropy of the reactants, please don't forget to multiply by the number of moles of each substance. The same thing has been listed over here. So entropy of the products will be X, because I have X moles of X. So X into the entropy of X plus Y into the molar entropy of Y, and so on and so forth for the products, minus the number of moles of the reactants M multiplied by the standard molar entropy of M plus N into molar entropy of N, and so on. The numericals based on this are very, very easy. I would sincerely advise you to practice these numericals after watching this video. You face any difficulties, most welcome to ask your doubts in the comment section. Coming to various other processes, thermodynamic processes, which we have discussed in our earlier videos as well. Isothermal process taking place at constant temperature. So delta S is Q reversible upon T. Now Q we know is 2.303 RT log of V2 by V1 divided by the absolute temperature. So our expression gets rid of T, and we have the expression for change in entropy for an isothermal process. Isobaric, the enthalpy change is taking place at constant pressure. Isochoric, the process is taking place at constant volume. So if you remember, we had spoken about the specific heat capacities at constant volume and constant pressure. The same we use to derive an expression. The detailed derivation is not required at this stage, but yes, if you want to go ahead, we just integrate it within the temperatures T1 and T2. So this gives us an overall view of the entropy changes, and this should be more than sufficient for you to attempt numericals based on this. Coming to the term standard entropy. Now we have been using this term standard for a long time now. Past almost 12-13 videos we've been talking about standard. Standard means you take the substance in the standard form at temperature of 298 Kelvin. The entropy of the substance in its standard form at 298 Kelvin is what we call as standard entropy, and we denote it by the sign S naught over here. Third law of thermodynamics, just related to your daily life. When you are awake, you're moving around, you're thinking, you're working, you're writing, there's lots going on. So there's a lot of random movement which is taking place. You're restless, there is disorderliness. Now when you go to sleep, everything soothes down, quietens down, the disorderliness, the thought process slowly becomes less, right? Third law of thermodynamics relates to that. What it says is that you have got substances in gas, liquid and solid. In the case of gas, as we discussed earlier, the particles are in a state of continuous random motion. They are far away from each other. There's a lot of disorderliness. Liquid, the particles are a little closer. So what if I decrease the temperature of the liquid and turn it into a solid? Here the particles come even closer. In other words, their possibility of getting disordered keeps on decreasing as I am changing from gas to liquid, liquid to solid, till we reach a stage where I have a perfectly crystalline substance, right? A substance which is completely at peace, completely quiet. There is no disorderliness. In that state, because there is no disorderliness, we will say that the entropy of the substance in such a state is 0. And this was given by Nernst. Practically difficult to achieve. Theoretically, yes, this is achievable at absolute 0, right? So entropy of a perfectly crystalline substance at absolute 0 is 0 according to Nernst. So what's the point of this? If it is 0, then what is the point of this? Yes, the point here is it serves as a reference, as a base. Now I know that at 0 Kelvin the entropy of any substance is 0. I can then compare the entropy of the substance at different temperatures, having said that at 0 Kelvin it is 0. So this serves as a reference point. If you remember, when we talked about internal energy and enthalpy, we said that there can be no reference point. There all the time we were doing the change. Whereas in the case of entropy, what is there is we've got a reference point of 0 Kelvin when the entropy of the substance is 0. That is where the third law of thermodynamics comes in useful. It helps you to calculate or determine the entropy of the substance at different temperatures. Please subscribe to the channel if you have not done. Request you to share it with your friends, because my basic motive of making these videos is to be able to reach as many students as possible so that they can benefit and they can enjoy learning chemistry. Happy studying to all of you.